So I want you guys to remember to be consistent with the text in that multiple regression, when there is a non-significant variable, it should be removed and the regression should be run again. He's expecting you guys to do this in your final exam. And that's just a second question. But remember, so if you guys find in your multiple regressions, if one of your variables is insignificant, I want you to drop that variable, rerun that regression.
How about the outliers?
Does he want you to drop outliers consistent with the book?
He's never said that.
We did a few, no?
We never actually dropped him.
This was not this one too. Okay.
Well, unless you have a really good reason.
I would say no unless we know there's data error. All of the data you're going to get is probably not going to contain data errors. So I would say no for now, and then we can ask him during the final. Because he'll be here for the final, right? You guys all do it together. As a group. But not as a group. Okay. Let's all turn to page 429. And there we will see question 21. Okay. So question 21 says, Fowl Marketing Research Incorporated bases charges to a client on the assumption that the telephone survey can be completed in a mean time of 15 minutes or less. If a longer mean survey time is necessary, a premium rate is charged. A sample of 35 surveys provided the survey times shown in data file named Fowl. So if we go to chapter 9, we go to our Excel files. Chapter 9, there should be one called Fowl. There it is. It's just a bunch of times, and there is 35 of them. Based upon the past studies, the population standard deviation is assumed to be equal to 4. So our standard deviation of our population here is equal to 4. Is the premium rate justified? So currently, whenever a premium rate basically what's happening is here is this marketing company is advertising this survey time of 15 minutes. And so they're trying to offer a standard pricing of 15 minutes. And whenever the average time goes above that 15 minutes, they're going to charge a markup to their survey time. So if they're being fair and they're being honest with their customers, then their real survey time should be 15 minutes or less. So to test whether or not this rate is justified, we should test
Greater than 15? Is that alternate?
think about this. This is interesting. Let's take it from this standpoint, the standpoint being that if we're trying to prove that the rate is not justified. So we're a client with, this is not, the question's not specified, great, this is how we'll approach it. We're a client and we're doing business with Fowl Marketing, and we believe that the rate is not justified. So to prove that the rate is not justified, we have to prove that the mean sample time is greater than 15 minutes. Now, if the mean sample time is truly greater than 15 minutes, then this flat rate they're advertising with the markup, if the survey goes long, isn't really a flat rate. Really, the survey is always going long. We're always going to be paying a premium instead of this flat rate. So if we're testing that if our alternate hypothesis is that the mean is greater than 15, our alternative hypothesis is that the mean is less than or equal to 15.
Mm-hmm.
And this is going to be a right or an upper tail test. Now, given the information that the question gives us, are we going to be doing a t-test or a z-test here?
Z.
Z. We're doing a z-test, and the reason why is we're given a population standard deviation. So if we're given that, we don't have to use a t-test, we can use a z-test. So we're going to use a z-test here. And for your final, Dr. Steele said you guys aren't going to use any of the templates. So we're just going to be using all of the testing functions built into Excel already. So we can go to data, data analysis, z-test for 2 sample, or wait. Never mind this question. Actually, this was on your midterm, wasn't it? These types of questions were on your midterm, right? Testing the difference between one and the other.
Oh,
So skip the first one.
He said that he's not gonna answer his questions where we have to use the template.
Yep. So this is a midterm question. So ignore the first question.
Okay.
I'm not gonna do that.
What?
I'm not gonna do that.
Don't do it.
Okay, so
Yeah,
next,
we're not doing that.
so we jump to the page 500 or you
So go to
have-
page 498.
I'll let you know.
So for 498, mutual funds are classified as load or no load funds. Load funds require an investor to pay an initial fee based on a percentage of the amount invested in the fund. No load funds do not require the initial fee. Some financial advisors argue that load mutual funds may be worth the extra fee because these funds provide a higher mean rate of return than the no load mutual funds. A sample of 30 load funds and a sample of 30 no load mutual funds were selected. Data were collected on annual return for the funds over a 5-year period. The data are contained in the data file mutuals. This is chapter 10. The data for the first 5 loads are as given below. Let's open up our data file first. So we're getting 2 sets of samples. One is for load mutual funds and one is for no load mutual funds. So formulate a hypothesis such that the null leads to the conclusion that the mutual funds have the rejection of the null. So we want to test whether or not load mutual funds truly have a higher rate of return than no load mutual funds. So if we're trying to prove that load mutual funds have a high rate of return, then the average rate of return for load mutual funds greater than the average rate of return for no load mutual funds is going to be our alternative hypothesis. So whatever we're targeting to try to prove, we're going to put that in our alternative hypothesis. Our null is going to be opposite of that. This is going to be a right tail test, left tail test.
Does it say low there?
What load and no load. So on the left-hand side, these ones are the load mutual funds. So the question does not give us a population standard deviation. So if we do not have a population standard deviation, are we doing a t-test or a z-test? T-test, yes. So we're going to go to data analysis. Two tests, t-test for two samples, assuming unequal variances. Remember in this class, we're always going to assume unequal variances unless specified otherwise. Arrange one, we will do, actually, let's do this. Let's change this to load and this to no load.
No matter which one's 1 and 2.
Nope. Doesn't matter which one you highlight, 1 or 2. In your templates, it did matter, I believe, so, but here it doesn't. We're just doing the data function.
And how do you know to choose unequal variances?
Always assume for this test and for this class that we're going to do unequal variances. So really the only choice we're going to make on these type of tests, on which test to run, we look at our options we're given. We're given a z-test 2 sample means. This is we're only going to use this if we're given the population standard deviation. And then if we're not given this population standard deviation, we're running a t-test, and we only really have 2 options. It gives us 3 options, but we're only going to use in this class either a paired sample or just unequal variances. And paired samples, remember, is one person or one thing spitting out 2 different data points. So one kid taking 2 tests, one machine producing 2 items, one barista making 2 drinks, however you want to think about it. But they have to be paired, a paired sample there.
And the sample means is when you have, what did you say, population?
For which one?
Or the sample mean, the t-test sample means? The first one?
The z-test, you mean? If we're given the
t-test.
population standard deviation.
No, you showed 2 t-tests. I missed what you said earlier. Sorry.
So there's 3 t-test options.
Uh-huh.
We're never going to use assuming equal variances.
Correct.
So 2 for paired sample, it has to be a paired sample, and then if it's anything other than a paired sample, we're going to assume unequal variances. So we see that the return for load mutual funds comes in at 16.22, and the return for no load comes in at 15.70. So just looking at the means, it would first appear that load mutual funds are giving us a higher return. But when we look at the variances, both of them have very, very high variances. And when we run our actual t-test to test whether the 2 means are statistically different, we look at our one-tailed test p-value, and it's 0.279. So 0.279 is greater than the alpha value that's specified of 0.05. So we would fail to reject the null, or we would accept the null, as you guys like to say. So we'd accept the null. So basically what we've proven is that there's no statistical evidence that load mutual funds have a higher return than no load mutual funds.
I
Yes.
thought it came out greater than,
What?
I thought it came out greater than, like the mean was greater than the 0.27.
So the mean was greater, yes. But when we factor in how much variances are in the 2 populations, they're close enough where we can't say they're statistically different from one another. So this one's coming out with a return of, let's say this percent, 16%. This one's coming out with a return of 15.7% on average. But there's so much variance between the 2 populations, we can't say for certain that the 2 populations means aren't actually.
So that t-test scored 0.279 because it's greater than the 0.05.
Because it's greater than, we accept the null. So when your p-value is less than your alpha value, then you reject the null. And when your p-value is greater than the alpha value, you fail to reject or to accept the null. That's a good point to make.
So p-value less than alpha, we reject.
Yeah,
P-value,
if p-value is less than alpha, we reject the null. If p-value is greater than our alpha, then we accept the null. And remember, the reason why we set this test in the first place was stockbrokers are trying to sell people on the fact that we get a higher return on load mutual funds than no load mutual funds. So they want to prove that load mutual funds have a higher return in order to justify the cost that they're charging the consumers for those mutual funds. But this test has shown us that there really is no evidence of that difference in the two returns. So there's no evidence in the difference in two returns, and buying the load mutual funds isn't really worth it. Okay, so what if we got a similar question to this question right here, but instead of not specifying what the population standard deviations were, they said the population standard deviation for load accounts we know is 10, and the population standard deviation for no load accounts we know is 9. So if the question were to specify population standard deviations, what test would be run instead of the test we just ran? A z-test. And so what's the difference here when we're running it operationally? Is we take the z-test, is going to ask us, so we're going to do a z-test for two sample means. So again, we highlight the load mutual funds, highlight the no load mutual funds. And then we have to remember specifically which variance is attached to which set of data. So for our load mutual funds, we said the standard deviation for the population is 10.
It should be 100.
And for the no load mutual funds, we said the standard, variance. Our variance would be 100. We have to square our variance. And so for our no load mutual funds, we said the standard deviation is 9, so the variance would be 81.
Yes, because
Excellent highlight C. My bad. There we go. So
I did not get the option that you did on the variance below the variables.
which one did you select?
The pair two sample means.
No, we're doing a z-test
Oh, I'm sorry.
for two sample means. So paired two sample means, we would not know what the standard deviation of the population is.
I would question on, so we say, I guess I have a hard time understanding when we look at just the p-value and say you always reject based on the alpha. Because like, let's say for example, we just flip-flop the data, right? If the load became the no load, no load became the load. Your mean on the load would be lower than your mean on the no load, but you still have the same p-value.
For the one-tail test or two-tail test?
Well, I guess either.
So the one-tail test, when you do it in Excel, it targets what should be the correct one-tail test. So remember how in your templates you had to run run an upper tail and a lower tail? Excel is smart enough to know which one-tail test to run.
Well, I guess what I'm saying is, so your mean for the
Mhm.
load would be lower than your mean for the no load. And if we structure our null like that, we would say, oh, reject the null because it's not significant. But we're rejecting if the mean is lower, even though our average proves that it's lower, right? So we're saying that no, it's not. It's not lower. But I guess that's what I'm saying, is like you wouldn't know. You don't know what you don't know the mean, you don't know the, like, I guess if you just switch the titles there. No load is 15
Mhm.
and load is, I'm sorry, yes. No load is 16 and load is 15. Well, that matches our null, but we would reject it because we say it's not significant. So I guess when I say.
Yeah, so what you're saying, I kind of get what you're saying. So you're saying that it doesn't, this structure,
I guess what I'm saying is you can't just blanket look at your p-value without knowing what you're rejecting. You know, because like here pretend we're in my fantasy land where the means are flip-flop, right? So we're saying that the mean is lower in the load, which matches our null. But then we're going to reject it because we say it's not significant. Does that make sense?
You're really testing for the H1.
so here, our mean does, we're testing,
Yeah, so I think what he's talking about is, let's say it was significant.
Or sorry, if it is.
Yeah, let's say it is significant.
Maybe that's fine.
You would have to look at the means to know whether you're rejecting or accepting.
Yeah, exactly. I guess that's what I'm saying. So you're right.
Because like, so
I
if it was
meant if it was
significantly different,
significant.
you would have to know which one was higher or lower to whether you're rejecting.
Right.
Because if it was lower, then you'd be.
Because we do this in class and we don't even know what the null hypothesis is. We look at this and we're like, reject, accept. But then it's like, we don't know half the time what we're trying.
Oh, so you're saying like it could say no load is
Sorry, yeah. So
greater
pretend
than.
again in my fantasy world that the load is 15 and the no load is 16. And then it is significant. But then we say we accept the null, but
And failed to reject.
we fail, but we're proving in this situation that the load is lower.
I'm a little confused with your reasoning. But let me,
I don't
so
know, I don't
let
know how
me,
to explain it well. I guess what I'm saying is, I get concerned or confused by saying, anytime you see something that is significant, you have to reject because you have to also look at what you're measuring. So in this case, we would pretend like the p-value is significant. In this scenario, we would reject, and we'd be all good. But if those were flip-flop,
so if we swapped those results here, but we kept that hypothesis the same,
yes,
yeah, we would reject that.
yeah. So
Yeah.
that's what I'm saying is like you can't just say like look at the alpha, and if it's less than whatever our, or look at the p-value and it's less.
Here's
than our
what the
alpha.
real solution to what you're saying is that you should just always run a two-tailed test. And then if you run a two-tailed test and one mean is greater than a mean and you reject the null, then logically the one is greater than the other. Because what we do is we essentially take an estimate. What we're doing here is we're building a confidence interval for what we think the mean is. And when we do a one-tailed test, we're testing whether or not these two confidence intervals cross paths with each other. So what we do is when we run a two-tailed test, we essentially say that these two confidence intervals can't touch ever. And so if they can't touch ever, and we prove that, and then we can look at this mean and say this mean is greater than this mean, then we know statistically that this population has a greater mean than that population.
Right.
That's the logic of kind of your, I think, solving what you think your issue is.
I think I don't know. I think what I'm saying is like we've been conditioned to just say look at the p-value.
Yeah.
If it's less than the alpha, reject. But I think it's more complicated than that because you have to know what you're measuring.
Yeah, you know your hypothesis.
Yeah, you have to know what your hypothesis is.
Mhm.
Because this was probably part of the confusion of the midterm one where the mean was higher, but then we rejected. It's really weird. So what I'm saying here, I guess, is there's been circumstances in class where we don't even know what we're measuring. We just run the test and we're like, reject.
Yeah.
And we're like, it's significant. But what if the mean is different? You know, what if we structure our null hypothesis like this?
Like in that one question that was messed up.
Yeah. So I guess.
So I think the best way to go about, I guess what you're saying is you always should structure your hypothesis test based on your business. The thing about in a business sense, on your business issue. So I have a business problem I'm trying to solve, and that's why I'm running this test.
Uh-huh.
And so my business problem is I want to make an investment in one of these two mutual funds. I got a guy who tells me these more expensive mutual funds is a better result for me, and I'm going out and testing that business question. So your hypothesis should always be set up based on circumstances that you think you're trying to prove or trying to disprove.
So you could even just, like what he's saying, if you flip those and just the mean tells you that that's wrong.
No, yeah. So
You
if
stop
so,
there,
just
right?
here, yeah.
If
If,
I got a higher mean.
yeah,
I would
if,
stop.
if we're in the same circumstances where someone's trying to sell me these low mutual funds against these non-load mutual funds, I look at the average of 30 annualized return rates, and I see that no load is greater than load, and I'm
But
gonna say,
I don't look at the
yeah,
p-value. It's just
I'm gonna
dumb.
say, listen, I know there's no possible way that if I have enough data, this is gonna be
So
statistically.
basically, it's like a two-step process. Step one is, does it pass the first test in that?
Yeah, it's like a sanity check for what you're
Right.
doing.
So then if it's, because we kind of just assume automatically that it passes that test. I think that's right. That's what
That's
we
how we
have
done
to
in
do.
class, yeah.
That's how we kind of learned it. So I guess that's why I was.
Yeah, there's always a sanity check of when you're trying to test these two things. Usually this
Sorry.
mean should be greater than the other mean. So one mean should be greater in order for you to even be wanting to run that test.
Right, yeah, okay. To even look at the p-value, you gotta say, pass this gate.
Yep.
You got this, buddy.
So now for this, what was the hypothesized mean difference
I
and
was
the
Zero.
Zero?
Zero for hypothesized mean difference, and then variance, we went off the population standard deviation of 10, the population standard deviation of 9. So variance is those two numbers squared. So for load, it was 100, and for no load, it was 80. Okay.
Like, I still have no idea what you're talking about.
They're better at explaining than I am.
Okay, let's move on to page 500, question 46.
I can't find the data file for this one.
Computer news.
Is it in there? Does anybody else have it?
It's not in there.
Oh, yeah, that's true. Well, the last chapter.
No data.
Okay, let's just set up the hypothesis test for this then. So, American Press Institute reports that almost 70% of Americans use computer to gain access to news. Suppose you suspect the proportion of American adults under 30 who use computer to gain access to news exceeds the proportion, bless you, exceeds the proportion of Americans at least 30 years old who use a computer to gain access to news. So, first thing that they say is that we think we have a hypothesis that the proportion of under 30 US adults who gain their news from the internet is going to be greater than the proportion of over 30.
And there's no population standard.
Yeah, we're not given a population standard deviation, and this is a test of proportions and not a test of means. So let me do one quick check to make sure if this is on.
But it's only two proportions.
That's not two proportions.
So if we have the data, we have to get the mean. And then
So, I guess let's skip this one.
We can get it on the test.
This may be exactly like you. You can do the one that we did earlier.
I might write an essay about what you wrote.
Just be a big.
So this one's we've only solved this one using a template, so this one's not gonna be on your test. Right? You guys were in class, I wasn't. No templates.
So we would do a proportion with 3 or more, but not with.
Not just 2. So speaking of proportions with more than just 2, if we go to page 560, question 30, an ambulance service responds to emergency calls for 2 counties in Virginia. One county is an urban county and the other county is a rural county. A sample of 471 ambulance calls over the past few years showed the county and the day of the week for each emergency call. The data is below. Test for independence of the county and day of the week. So that's called ambulance in chapter 12.
I cannot find it.
Got it.
You did?
Mhm.
Where was it?
Chapter 12.
Chapter 12?
Mhm.
Is it ambulance?
Mhm.
I don't know.
I don't have it.
Don't want to share that.
Can you send it to
That's
us?
a shared drive.
Let's go on the webcam.
Google Drive.
The beauty of that is they gave it to us already in the book, so I don't need that. So
No, but I don't have it.
it's in your book. If you look in your book on page 560, you're gonna have all the information you know.
Yeah, it's on our Google Drive.
Is it?
Mhm.
I don't know.
Cohort 16?
Mhm. No, it means the teacher probably took it off. I know, so Bob downloaded it before the professor took it off.
Okay,
So.
So-
Process that for you and I.
I'll see if I can find it.
Chapter 12.
Cohort 16. Stats. Yeah, we just had this whole discussion.
okay. So this is what our average times look like by county and by day of the week. So what we're doing is we're testing independence between county and day of the week. By that, I mean, is there some sort of relationship between county and day of the week? Are some counties slower in certain days of the week? Are some counties faster in certain days of the week? Or are they all completely independent of each other? And do we have the same times throughout the week? So I sent you guys a final exam review guide. Sent it back to you guys a while ago. In your final exam review guide, I would keep this with you. Just have it on your desktop homepage or wherever you have it. Because for chi-squared tests, I built you this pre-built chi-squared matrix.
Mhm.
So what we can do here is we can take these variables that we were given, and the way we get these variables from data is we build a pivot table. We put county in the columns, and we put day of the week in the rows. We can take these values, we can paste them into the upper left corner of our chi-squared matrix that we have pre-built. And it's going to generate us our expected values for us on the table below. So what these values are is if there truly is independence between Daily Wake and County, this is what our values would look like. And now we're going to test for a statistical difference between the two. And we do that by doing a chi-squared test.
A little fast on this one. Like, just slightly.
Just under there.
It's open itself.
Yeah.
I'm trying to find the file.
So if you don't have the file, just copy the values from your book, like I did. You can make your own table. If you have the file, you just make a table that looks just like this using a pivot table.
Yeah, can you scroll over to the left?
Yep.
Oh, the other one. The other one.
I see how you built your stupid.
What?
Yeah, I got it right.
Built what? Which one?
No, it actually turned out amazingly, so.
Oh, this, I just copied the values from the book.
Ah,
So what you do is if you have the actual data, you pull them into a pivot table, you pull county into columns, and you pull day and week into rows.
exactly what I did.
Good job. So then we don't pull any of the totals, we just pull the values and we copy and paste them into the matrix that at first is going to have all zeros. We're going to copy and paste it into that matrix. And when we do, the matrix below will populate with our expected values.
Did you just do like the first 10?
What?
I'm sure like 172 lines.
Of what?
I was like on the ambulance.
Yeah, you have to do a pivot table. So I didn't have the data, so the book already made a pivot table for me. The book already made a pivot table for everyone. And your pivot table should look like this blue box on page 560.
Well, but on the test, how do we go through that? Like you know what I mean? Like I would probably tackle it differently. You know what I mean?
Oh, man, that's it. This is like a mix of the old. Okay, so this is a similar one. Here we have data. For men and women and what their beer preference is. So we want to see if beer preference is independent of gender. So does your gender determine the type of beer you like to drink? Or does the type of beer you like to drink, is that independent of your gender? This one's called beer preferences. It's in chapter 11's data. So we put this into a pivot table. So we're wondering, is gender independent of beer preference? And you can pull, so we pull one categorical variable into rows, we pull another categorical variable into columns, and then we pull another variable into values. We want to do a count of these values. So we're trying to test whether these proportions are independent from one another. So this is what we get for our beer drinker example. So we would take the values from here and go back to our chi-squared table. We paste them in here, and then we have to convert everything that's not from that table to zeros. So then we run a chi-squared test. The chi-squared test, we highlight our actual variables, and then we would highlight our expected variables, and we get a p-value. So our p-value here is less than 0.05.
Is that a p-value or not?
Yes.
Yes.
You guys are tough.
That was the one that.
Is that part of the template? But it's not on mine.
No, you have to run, you have to type in chi-squared test. It's not part of the template because the area that you select changes from question to question.
I'm pretty sure that's p-value. Yeah, that's the one that.
That's a p-value. It's p-value. But the reason why it's not on the template is because, remember, you only select the values in the same metric matrix that you show.
Okay, hold on. Hold on.
3.
Oh, yeah, that makes sense.
Last time.
I want to copy that. And then I want to paste it there.
The chi-square test is the highest chi-square dot converge dot like
How do you get p-value?
the p-value.
That's a good idea. How do you get the p-value?
P-value is just, okay, yeah, you're right.
Okay.
Chi-square dot
so-
test. You highlight the range, the original range, as your first range. Let's go back to the
Test.
range as your.
That's the p-value or the chi-square?
To get the p-value.
So we always get
To get the
chi
p-value,
test,
you
we don't get
use
the
chi-square
other
dot test
kind.
once.
Oh, I did it backwards.
What are they? Which one?
Well, they're like
It's saying
distribution,
to do this,
distribution
do that.
right, inverse. I just want to make sure
I'm
that
just
I'm
telling
getting
You
it
don't do that.
right.
So for this one,
Mhm.
if they ask us for a p-value, we want to test for independence, or test for dependence, then it's always going to be chi-squared test.
So then,
Six.
so then, chi-squared, how do you get that?
17.
Ah,
So
see?
both ranges.
So you
Okay.
work backwards. It's like Excel's like, I'm gonna put the bullshit. We can't give you a p-value. is what
So
you're
I got that p-value.
Oh, that makes sense, then, because it needs a probability.
So this
I know what
tells
you're after.
us that it is significant since it's less than alpha.
Yep.
Correct?
So
How do we figure out the free range? Something minus something.
It's rows minus 1 times columns minus 1.
Oh, it is?
Rows minus 1 times columns minus 1.
That's right.
So for the other one, was it significant? The first one that we did?
I didn't finish it, so I'm not sure.
Oh,
So our null hypothesis for all of our chi-square tests,
Rows minus 1 times columns minus 1. So here's like 1 times 1, 6.
so always for our chi-square test, our null hypothesis is that all of our proportions are equal to one another. And our alternative hypothesis is that our null hypothesis does not hold. So if all of our proportions are equal across the board, then all of our proportions are independent of any sort of categorical variable. What we found is that we rejected the null. So for this one, we found that beer preference is, we're going to reject the null because it's going to be lower than their alpha. It was 0.4.
He's still looking at beer preference.
So you need to go back, you back on the, you need to go back.
I haven't come back. I'll finish that one in a second. But just because people want to see how the data works. This one is 0.04. So this one we would reject the null. So we'd say that there is dependence between gender and the type of beer that you like to drink. So a greater proportion, we can look at this data and see that for light beer, I think.
Dark line is regular.
So versus our expected proportions, women dislike dark beer and they like light beer more versus our actual expected proportions. So let's finish the first question we started with. Ambulance is the day of the week.
Hold on, can I ask you a quick question? When we say the null that we're rejecting, is because what is not equal? P, like proportion one, what would it be? We're talking about each type of beer?
So what we're saying, so our null hypothesis is that all proportions are equal. So if all proportions are equal, that means that all proportions are independent of how we segment the population.
So I can go home and say, honey, you definitely like beer more or less than me, but I can't tell you which one.
I don't know about that statement. Wait, so if this held, no, if your null held, you could go home and you and your wife would equally like all kinds of beer. So there's, if you both like light beer, you both probably wouldn't like light beers and like dark beers. There's this, you would both like whatever the type of beer it is.
We can share.
If we reject the null, we're saying that you and your wife have, you and your wife have different taste buds. So your taste buds are dependent upon some sort of factor within yourself.
So how would it look if we accept the null? How would it look? Like, what are the numbers? Like, how would they? I know that it's the opposite of what happened, but help me understand what would be the opposite. In which scenario we would say, okay, we accept the null.
Okay, so let's just finish the other problem that we started. So the other problem we started was we're testing for ambulance times, and we're testing for dependence between area of county and day of the week. So we copy in our actual values. The matrix calculates our expected values for us. We then run our chi-square tests, but we have to highlight the proper values.
So if I'm wrong,
So you reject that.
I'm gonna have to check that.
So we highlight the proper values. We end up with a p-value of 0.4039. So our p-value is going to be greater than our alpha value of 0.05, which means we're going to accept the null. We would accept the null. So we'd say that all proportions are as expected, or all proportions, the wait time in each county is independent of the day of the week.
See that condition, wait times.
So the wait times are independent, in each county are independent day of the week.
That's the choice square number.
It's
It's
a
called the
p-value.
chi-square value.
Yeah, he's asked us to do that a couple times.
So we'll go over that right now.
Oh,
Together, make it p-value.
It's a sum of the differences, right? So it really doesn't, you can't compare one chi-square test to another.
It's good if they have the same.
Totally different data.
Yeah, that's standard. Yeah.
Okay, so if he asks you to solve for your chi-squared value, then we're gonna use our chi dot inverse. Let's calculate degrees of freedom. The degrees of freedom is going to be rows minus 1 times columns minus 1. So rows times columns minus 1 for this one is going to be 6.
So on homework 3, we used, for that formula, it was chi-square dot inverse 5 by 2. Because a different number, of course.
I think it's 1 minus, right? No? Oh, yeah.
so
Homework
we
three,
need
John.
is the probability plus degrees of freedom.
How would you do that?
1, 2,
That's what I want to know.
so
It's getting harder and harder to find that out.
is it 10.03? Is it 10.03?
No, what? Is what?
The, oh, not for this one, I'm sorry, for if anyone is working on the beer example. You didn't
I
do
think
it?
we did 1 minus. We made it. Like, because we just said the.
Why would you ask?
Okay, so this is called chi test value, chi value,
I can think of it that way, and I'll never forget it.
I guess.
What? Forget what?
My sexual test. Yeah, either way.
Who's that way looking
You're
at?
very visual. I'm so glad. my-
You're very progressive statistician. I am a visual learner.
There's a background, that's just-
There's a background. Oh, I don't think
Yeah, but not very many people like that.
Roundabout way.
Oh, I like it. Eric's blushing.
We're always good on the phone.
Is this what I missed when I don't come to class? That was 5%. Hi there.
I asked a question. He's not stopped to search. Okay, thank you. Bye.
I'll tell you, leave it for us.
We only had it one time.
We like immature. Yeah, we like, well.
And how much are the
Sorry.
What does it look like by Saturday?
Oh,
It's gonna be a lot of people.
I feel like the answers are next. I feel like the answers are next. Huh? That's it. Just so I can- Unlimited.
I was telling my.
Like going through the first, so it's curious, on purpose, so that you can just be
Yeah, use your right tail. Chi-square inverse dot right tail. So if he asks us for our chi-squared test statistic or our chi-squared test value, we're going to take the chi-squared inverse dot right tail of this chi-squared test, our chi-squared p-value, and if he asks us for a critical value, we're going to do chi-squared dot inverse dot right tail of whatever our specified critical value, it's usually 0.05, comma, or,
Then you just use the p-value.
The p-value.
You just calculate it.
so this is a critical value. So this is different. We asked you for a chi-squared test statistic and a chi-squared critical value. So remember we have our t-tests and then we have our p-value tests. So this is the same thing with chi-squared. There's a chi-squared p-value test and then a chi-squared critical value
This is
test.
basically just from a table.
Yep.
You can look it up. in a
You can look
table.
at a table if you want to as well.
Okay.
But if you don't want to look at a table, you just want to do it in Excel, you put your alpha value in. And since our alpha value of 0.05 with degrees of freedom of 6, our critical value is 12.59. Our critical value, and then our test statistic is less than a critical value. If your test statistic is less than your critical value, you fail to reject the null, or you accept the null. Remember, for critical value tests, we always want our test statistic to be greater than our critical value. And for p-value tests, we want our alpha value to be less than our p-value to be less than our alpha value. Yep.
Again, the first formula we got 0.403.
It was chi-squared test of our two highlighted areas.
Okay, so that's just to get the p-value.
Let's get the p-value.
And then the other two you do inverse.
So the inverse dot right tail. Yeah. Inverse dot right tail, and remember that your degrees of freedom is 1 minus rows times 1 minus columns. What was your question? Someone had a question, right?
Would you show the formulas? and make this-
So that 6.17, the chi-square number, that's the sum of the differences between the test values and the expected values, right?
Some of the differences squared.
Some of the differences squared. right?
Yep.
So you can actually go in and come out and make,
Yep. You can just have a table and do it in the table. Yep.
and then does that number really?
What?
Does that number 6.1?
It's just if
It's just the sum of the square.
if before we could easily calculate what the p-value was for if you had to calculate by hand and you weren't allowed to use your Excel functions, then you would take this chi statistic, and you compare it against this number that we find in a chart.
Oh, and it would tell you.
And it would tell us, we would just make our decision, reject or fail to reject based on this. Since we have the computational power of Excel, we can just figure out what our p-value is right off the top.
Whether it's 6.1 or 25.2, I mean, if you're looking at that.
Because it's all that matters, all depends on your degrees of freedom.
All right.
So for this, like a simple test, a 6 might be okay. But say we are doing a column of 8 and rows of 7, we're dividing populations out by that much, well then your 6 probably isn't going to be good enough to cut it down. It's probably, it depends on the size of the degrees.
So now the first one is the p-value. The one after the 6.17, that would be the chi-squared Chi statistics.
Your chi-test statistic is here.
That's fine, so really.
This is the chi critical value.
Chi.
I don't want you.
Right.
Back to the So page 590. So the International League of AAA Minor League Baseball consists of 14 teams organized into 3 divisions, north, south, west. Following data show the average attendance for the 14 teams in the International League. Also shown are the team's records. Wins are denoted by W. L denotes number of games lost, and percentage denotes winning percentage. So this should be in chapter 13, data file AAA.
Did you say 15? 13. Triple A.
It's under T for AAA.
Thank you, Bob. I have tire as the last
Someone
one.
email it to me. I have all these, but
Did you say T for AAA? I have tire. Tire rack. That's the last one for chapter 13, right?
Mhm.
So let me check those numbers.
Yeah.
I'm not on that. Is anything about
so what we need to do here is we're trying to test the difference. Our hypothesis test is we're trying to see if there's a difference in attendance between cities. So our null hypothesis would be that attendance, the average value of attendance by division, the average attendance in the North Division is equal to the average attendance in the South Division is equal to the average attendance in the West Division. An alternative hypothesis is that H null does not hold. So, if we're testing the difference between 3 different means, what type of test are we conducting? ANOVA, yes.
Yes.
You get it, Matt?
Yep. So, in order to run an ANOVA test, we have to split out the data not by rows, but by columns. So what we'll do is we'll take all the teams in the north, and we're going to make a new north column. And then we're going to make a south column, where we'll put the attendance for all the teams in the south. And then we'll make a west column. We'll put the teams for all the teams, put the attendance for all the teams in the west. You should end up with 14 attendances. So we've transposed this data from north-southwest into north-southwest horizontally instead of vertically.
Hold on. Matt.
Is this like, why do you have to do that? Is this always there?
Yeah, this is the only way Excel can accept these ANOVA tests. We either have to transpose it this way, or we have to make them separated by rows and just have them row-wise. It's easier to do column-wise. So, yeah, you can just copy and paste, it's pretty easy. Once we get this done, we're gonna go to data analysis, ANOVA single factor. We're gonna highlight our input range. Group by columns, we put labels in the front row.
Why is it single factor?
Because we only have one variable separating out the three populations, and that variable is what division they're in. So they're in one of three divisions.
We cannot open the file.
And we're only going to do single factors for this class. Single factor ANOVA tests.
Is there a way to do what you do with the pivot table?
Do this. I was thinking about, I don't think there is. Because pivot table is always going to aggregate it. And so I fear that if it's just going to kind of do, it's going to wonk it up.
So do you highlight the whole thing, or
Yep.
is there four that?
You're going to highlight these three. When they ask you for your area, it's going to highlight this whole area here. And even though these South and West only have 4 teams in their division, it's going to know that. It's going to tell you here that they only have 4 teams in their division. So if we look at our p-value is 0.01, or we can look at our f-value and look at our critical value. We see that f-value is greater than our critical value. Both of those give us the same conclusion. That conclusion is that at an alpha value of 0.05, we're going to reject the null hypothesis, that all the average attendances are the same. And so what we'd say, and the answer is not all, attendance is different. Attendance varies based on division, and that variance is statistically significant. If we look at the averages, we could probably figure that one of these three is the reason why there's a variance, that being the South, which has significantly less average attendance.
We rejected it because it's.
Yeah, so our F statistic is significantly statistically significant, and since it is, we're rejecting the null that all mean values are the same. We're saying that not all these mean values are the same. At least one out of these 3 mean values is different than the other 2. Questions on ANOVA tests? ANOVA tests are pretty easy. If we're testing the difference of means and we have more than 2 samples that we're looking at, then we're always going to do the ANOVA test, or we're separating the sample into more than 2 segments, we're going to be doing an ANOVA test. And the hypothesis, remember this should be pretty important too, hypothesis for ANOVA tests is that all means are equal, or your alternative hypothesis is that the null does not hold.
What's Fisher's LSD procedure?
Ignore that part. Didn't like that part.
What number was it? What question?
This was page 490.
590.
590. Nope. Yeah, 590, question
20.
20. So ignore part B, because you guys didn't learn part B. Basically what part B would be doing though is there's tests we can run. We can start testing the differences between each individual mean and see where the difference actually lies. Here, I'm not going to do it, but I could probably reason to guess that South is really the big difference between these two. There's a chance that north and west are the same, but there might be a chance that all three of them are different. So, page 607. Question 32 says, as part of a study designed to compare hybrid and similarly equipped conventional vehicles, Consumer Reports tested a variety of classes of hybrid and all-gas model cars and sport utility vehicles. The following data shows the miles per gallon rating Consumer Reports obtained for 2 hybrid small cars, 2 mid-size cars, and 2 hybrid small SUVs, and 2 hybrid mid-size SUVs. Also shown are the miles per gallon obtained for the 8 similarly equipped conventional vehicles. So, at an alpha value of 5% level of significance, test for the effects due to class, type, and interaction. So, first, with this data, does someone have this data sent to me?
Chapter 11? What? Chapter
Should we call it hybrid test?
Hybrid test.
Chapter 13 for you guys?
And what question was it?
It says 33 up there. but it's-
607, page 32.
32, not 32.
What is the name of the data?
Hybrid.
Mm,
What's your email?
yeah. Thank you. Who else needs this file? Just me?
So,
Thank you, Matt.
first thing to do is we want to test if there's a difference. We want to test if there's a difference by type. So if you look by type, there's only 2 different types. So we're not given a population standard deviation. So we can just do a conventional t-test for assuming unequal variances. Data analysis, we can do a t-test assuming unequal variances with our first range of cars being conventional cars and our second range of cars being hybrid cars. So, we're just trying to test for difference here. So, we'll set up our null hypothesis as the average miles per gallon for a hybrid being equal to the average miles per gallon for a conventional car, and an alternative hypothesis being that average miles per gallon for hybrids are not equal to the average miles per gallon for conventional cars. What's our two-tailed test p-value? 0.044, and that is going to be less than our alpha value. If our alpha value is 0.05 and our p-value is 0.045, that means we're going to reject the null hypothesis.
The t-test.
Yep.
With non-numerical.
So you have to highlight just the data values. That's why. So for this one, we have to first sort by type, and that gets all of our conventional cars grouped together and all of our hybrid cars grouped together. Yeah, unclick labels too, because you're not going to have labels in there.
That makes
Yeah, who's this? Or what you just meant that.
So, next thing we're doing is we're gonna test for class differences. That's going to be in an ANOVA table, yeah. Because type, we only had 2 types. We had convention or hybrid, and now for class, we have 1, 2, 3, 4 different types of classes. So, what we're going to want to do is we're going to want to make 4 different columns. And for each column we're going to populate, it should be 4 observations. So we should end up with 4 columns of data that look similar or look exactly the same to what I have here. And remember, we're testing the difference between multiple means, more than 2 means. And if we're testing more than 2 means, our hypothesis is going to look like this. Our null is that the mean for mid-size car is equal to the mean for mid-size SUV is equal to the mean for small car is equal to the mean for small SUV. An alternative is that our null does not hold. So we're going to go to data analysis. We're running a single factor ANOVA test. Okay, labels we separate by columns. Our ANOVA table should look like this. So our p-value for our ANOVA table is 0.005, which is going to be less than our alpha value of 0.05. So if our p-value is less than our alpha value, we're going to reject the null hypothesis. And if we reject the null hypothesis, that means that we know that there is some statistical difference between at least one of these 4 groupings of cars. The miles per gallon isn't the same. And we can look here and see that small seems to be substantially out of the range of the other groups. We're not going to do interaction because it's not going to be our test, but these are 2 types of tests that if we're given data with multiple categorical variables in the data, then we can be asked to run both a t-test if there's only 2 different breaks, or we can be asked to run an ANOVA test if there's 3 or more different breaks in the data. So, page 695, question 57. One of the biggest changes in higher education in recent years has been the growth of online universities. Online Education Database is an independent organization whose mission is to build a comprehensive list of the top accredited online colleges. The following data table shows the retention rate and graduation rate for 29 online colleges. Develop a scatter diagram with retention rate as the independent variable. What does the scatter diagram indicate about the relationship between the two variables? So if retention rate is our independent variable, then what is graduation rate? Our Y, our dependent variable, yep. So we're gonna highlight the two data sets. We're going to insert scatter plot. We're going to select data. And we're going to make sure that our X values is our retention rate and our Y value is our graduation rate.
Okay, check the 14.
Okay. So the next thing we can do, if we want to kind of look at,
Is that chapter 14?
Yes,
if we want to look at this relationship,
I emailed it to you.
You did. Thank you.
we can put in a trend line. So we can kind of see here that this relationship looks like a positive linear relationship. As our retention rate increases, it appears our graduation rate increases. So we can throw in a trend line, a linear trend line. And we can even include our equation and our R-squared value. So if he doesn't ask you to test for significance of the variables, and he just asks you to do a scatter plot, he might ask you to take these steps. First thing is draw the scatter plot. The next thing is to add the equation and the R-squared value. The equation tells us that there's a positive linear relationship between retention rates and graduation rates. Our R-squared value tells us that retention rate explains 44, almost 45% of the variation in graduation rates by itself. But in the book, it tells us to develop a regression estimate and test for significance with an alpha value of 0.05. So scatter plots won't give us a test for significance. So in order to do that, we have to do data analysis, regression. Remember, our graduation rate is our dependent Y variable, and retention rate is our independent X variable. And so when we run a regression, we see that our significant F, our p-value from our ANOVA table for our regression, is very, very small. And the p-value for our one independent X variable is also very, very small. So when we run a simple linear regression, this significance F p-value and this p-value for our single independent variable are going to be equal to each other. Our significance F p-value is telling us whether any of the X betas for our X variables is different than 0, whether any of them. And since we only have one, the p-value of these two is going to be the same.
How did you get it to read 0.00007?
So you can click on it, So it's gonna be in scientific notation, so all you have to do is click on these, just format them, and then just move out the variables till you start seeing some. So if we're asked to interpret our our beta for our x variable here, we can see that our data is in percentages, but it's in whole number percentages. So if we're in whole number percentages, a 1 unit increase in retention rate, a 1% increase in retention rate brings about a 0.285% increase.
Why did you pick X and Y that way? Because I did it different and I got different numbers, but I wonder.
So the book specified that your graduation
Is your
rate is your dependent, and your X is and your retention rate is your independent. And the other reason why was graduation rate is a later outcome than retention rate. So it wouldn't make very much sense to try to predict retention rate with graduation rates.
Right.
It seems logically it's a better idea to predict graduation rates based on the number of people that we retain. Yep.
The coefficient, is that beta 1 or beta 0?
So this is beta 0 and this is beta 1.
Okay, so this is
And then retention rate is x1. And retention rate has a statistically significant effect on graduation rate. And just retention rate, we're explaining about 45% of the variation in our graduation rates. Any questions? $754. The Tire Rack, an online distributor of tires and wheels, conducts extensive testing to provide customers with products that are right for their vehicle, driving style, and driving conditions. In addition, the Tire Rack maintains an independent consumer survey. Help drivers help each other by sharing their long-term tire experiences. The following data shows survey results, ratings on a scale from 1 to 10, with 10 being the highest, for overall performance for 18 high-performance all-season tires. The variable tread wear rates quickness of the wear based on the driver's expectations. The variable dry traction rates the grip of the tire on dry road. And the variable steering rates the steering responsiveness. The variable buy again rates the driver's desire to purchase the tire again. This data set should be called all-season tires. Or it could be called Tire Rack. It's called Tire Rack in my data. It could be called all-season tires or Tire Rack in their data. So first it says develop a regression, a simple linear regression equation that can be used to predict the buy again rating given tread wear rating. At a 0.01 level significance test for a significant relationship, does this regression equation provide a good fit to the data? So a Y variable is going to be whether or not a customer would buy again. And at first, we're going to start off by only using a simple linear regression. So our Y is going to be buy again. And our X for our first regression is going to be tread wear. We have labels. Here's our output.
So which one was your X? You did the first one?
Tread wear. So Y is buy again. So we're trying to predict whether or not the customer will buy again.
Yeah.
And what's driving that prediction is the tread wear rating from the customers. So our p-values, as we can see here, incredibly small. P-values are incredibly small. So we're going to say that treadwear has a statistically significant effect on the buy again likelihood of a customer. If we increase a treadwear score by 1 point, the buy again score goes up by 1.35 points. So buy again is super responsive to treadwear. People are really concerned about treadwear. And our R-squared tells us that treadwear explains 90.5% of the variation in the buy again metric. So it's a very good fit of a model for a simple linear regression. So next, we want to develop a regression that can be used to predict buy again given treadwear and dry traction. So first we predicted buy again with just treadwear. Now we're going to see, does dry traction give us any explanatory power in predicting whether or not a customer will buy the tire again? So our y variable remains the same at buy again. And our x variable becomes steering and treadwear. It's called steering in our data set. It's called dry traction, or a missing variable on our data
I
set.
think we're missing a variable.
Let's just, instead of it saying dry traction, let's just have it say steering. So the overall significance of this regression, if he asks you for the overall significance of a multiple regression, what we're going to look at is our p-value in our ANOVA table. So what this p-value in our ANOVA table is testing whether or not all betas are equal to each other. So our null hypothesis here would be that beta 1 for steering is equal to beta 2 for treadwear, and they're both equal to 0. And our alternative hypothesis is that our null does not hold. If we go back and we look at each beta value individually, treadwear, like we saw before, has a very, very small p-value. But steering has a p-value of 0.0299. And if we're going on an alpha value of 0.05, we would say we would reject the null. But this question in particular specifies that we want to go on an alpha value of 0.01. So an alpha value of 0.01, we'd fail to reject the null. And so we'd say that with an alpha value of 0.01, steering has no statistical significance. It does not have a statistically significant impact on buy again rating. What? Yeah, so you either remove it and run it again, or you can just, for this one, we can just go back up. Since we don't have dry traction for some reason in this data set, but let's just assume that it was. Let's assume our alpha value is 0.05. If our alpha value is 0.05, that means a 1 point increase in steering increases the buy again rating by 0.689. And a 1 point increase in treadwear increases the buy again rating by 0.9113. So based off the point estimates for beta, if we're a tire company and we want to improve the likelihood that our product gets bought again? Would we focus more on treadwear or steering?
Treadwear.
Treadwear, yep. Now let's do this. So, if he gives you one of these blank ANOVA tables, the easiest thing to always do first, the easiest thing to solve for, is going to be everything that pertains to observations and our degrees of freedom. So, our regression degrees of freedom is always going to be equal to the number of x variables we have in our regression. So we have 2 x variables in this regression, so our x degrees of freedom is going to be equal to 2. Our residual degrees of freedom is going to be equal to, if we add our residual and our regression degrees of freedom, we're going to get our total degrees of freedom. Or it's going to be equal to n minus 1 minus the number of x variables in our regression. So for this one here, we know it's going to be 15. And our total observations is always going to be n minus 1. So if our total observations is n minus 1, then we know that our observations is going to be equal to our total degrees of freedom plus 1. Our f value is equal to our regression mean squared divided by our residual mean squared. So our mean squared regression is going to be equal to our f value times our mean squared error.
Or it's sum of squares is also divided by degree of freedom.
Yep, or it could be sum squares divided by degrees of freedom, either one. For here, we know that our mean squared is always going to be equal to our sum of squares divided by our degrees of freedom. So our sum of squares is always going to be equal to our mean squares times our degrees of freedom. And our r squared is always going to be equal to our sum of squares regression divided by our sum of squares total. Multiple r is just going to be equal to the square roots of r squared. What's standard error? Someone figured this out last week.
It's the
Square root of residual mean squared.
Residual mean square. Okay, that's it. Oh, mean square, that's sum square. So these, I'm going to send you guys out a list of kind of these transposed formulas, because some people struggle with algebra. And then that way you guys can just know which one to multiply when. It'll just be like on a straight list downwards. I find these to be pretty easy questions overall. All you have to do is kind of remember this last one we forgot to do, F dot distribution of right tail of F, common degrees of freedom 1, degrees of freedom 2. Remember, you always want your degrees of freedom regression to be 1 and your degrees of freedom residual to be 2. And that's how you get your p-value for your overall test. Any question on filling out an ANOVA table? You guys should have your tab in your books, what page you're on. That's what I do.
And he'll have us do the bottom part too.
Yeah, for the bottom part, your p-value is always going to be your t-stat divided by your standard error. That's how you get your, your t-stat is always your coefficient divided by your standard error. Your p-value is always the two-tailed t-test. T-dot distribution of a two-tailed test. You're going to take your t-stat and then your residual degrees of freedom. We have to take the absolute value of your t-stat. If it's negative, and that's going to give you what your p-value is. And then you can just lock up this one here. You drag it down. You can see it's going to give you the p-value for, same p-value for all of these calculations. Any questions on this? Yep.
Not on this, but just in general, analysis, picking the dependent and independent variables, like Q's inside the question, like he's remembering class, he mentioned if something's predicting.
Yep. So if we want to predict something, if we want to use something to predict something, whatever we want to predict is going to be our y variable.
Which is this time.
So that's your dependent variable. If you want to predict something, it's going to be your dependent variable. Y. Y dependent, X independent. All of your regression should kind of make some logical sense. If we were using, it makes more sense for us on this one to predict the probability or the likelihood that someone's going to buy a tire again. That's something that we'd want to predict that'd be useful for us. It'd be weird for us to try to predict dry traction based on the likelihood that someone's going to want to buy a tire again. It doesn't make much logical sense. But the other way around does make logical sense. Let's see.
Could you open the formulas for me really quick? No, what is it?
If anybody hasn't seen Bob's ANOVA table, this is freaking amazing. Have you seen this?
Amazing. What is this? Equations?
You might not need to know.
So you might have-
Yeah. You might want to keep that for yourself.
Yeah, this is good.
Isn't that cool?
This is super helpful.
Yeah. Thanks, Bob.
That's on the team drive.
You can do that.
I just quite over
I never have to fill the blanks in. In the real world, that's like the Where's Waldo thing. I don't. Sorry, don't.
Where is that one? In the Google Drive? In the cohort?
Yes.
So going back,
Looks like that.
going back to homework 4, that's tab D with the S&P 500.
Yep.
Thank you.
I think a lot of us have still. like-
So for the S&P 500, remember, S&P 500 always is going to be your X variable. We're using S&P 500 as a proxy for market conditions in general. So we're saying how responsive is a single company to overall market conditions? How responsive is Microsoft? How responsive is SanDisk? How responsive is Caterpillar to fluctuations in the market?
The question says, comment on how much of the return for the individual cost is explained by, that's the same as saying predicted by. Like,
That's gonna be your R squared value.
oh, that's,
Yep. So how much of the fluctuation in each individual stock is explained by the S&P 500? That's gonna be your R squared value.
so where in this question do you like key on the fact that S&P 500 is your?
So in the homework you're given, you wouldn't be able to know that. But if you go to the book and you read the case study, then you know it from the case study.
That's the only predictor of the
Yeah.
all the other ones are.
In the book, it's like case study 1. I think it's in chapter 12, maybe, or 13. So it says case problem 1, so you can go look up that problem is in the book. It gives you kind of a big, long explanation of what's going on. Okay, so remember for your chi-squared tests, right tail to calculate your chi-squared test statistic. Yep, inverse right tail, I'd write that down. Chi-squared inverse right tail. Degrees of freedom is rows minus 1 times columns minus 1 for your chi-squared tests. That'll be on your test. What?
Where you going?
You guys cover multicollinearity?
No.
He mentioned it, but I don't think we went over in detail. It's when you have two variables that are
Yeah.
giving you two similar.
Let's read about multicollinearity real quick, just so in case that's a question.
That sounds like it's going to be. So is there any way, Matt, that you can kind of like everything that you just said that I couldn't write, that you can, I don't know.
Well, I'll be here tomorrow. We'll go over a separate set of questions. 728. So multicollinearity.
Yeah. It's over 0.7. So it's.
You're already wrong.
Yeah. Because it could be independent variables.
So, in order to test for multicollinearity,
Will he tell us to test for multicollinearity, or do we need to
He mentioned
just assume that everything has to be tested?
you'll be very specifically asked about it if he asks you about it. What's it called? Multicollinearity. Here's the idea of multicollinearity. If our x variables are correlated with one another, that's going to mess with our error terms. So it's going to.
Greater than 0.7.
So yeah, so if we run a linear collinearity test correlation test between two variables, and it gets over 0.7, your book says, and that's too much correlation between two variables. So what that's going to do is going to mess up all of your standard errors within your regression, and you could get falsely positive significance
So you
tests.
should only use one or don't do it.
So when you have them, so you should try to, in theory, you should probably try to kick one of the two of those out. You can live with multicollinearity. In some cases, you just have to specify it when you do. I don't think he asked you whether or not to kick them out. He just asked you to he just asked you about it. Just know about it. It's free. Your little couple paragraphs in your book is very simple. I just kind of read that.
Slide 14, chapter 13 of the PowerPoint.
Matt, the
Yep.
questions are more like, are the independent variables highly correlated? Something like that.
I tried an essay on
Is it an essay?
it.
No, yeah, he's in a blue book. Just no.
Something like, it'll be very specifically ask you whether variables within your multiple regression are correlated or not, or whether there's highly correlated variables in your multiple regression, and then it'll ask you, why is that a problem?
Oh, the Y parts.
Well, that's why we have to.
Yeah, 50% chance to.
You know, when you look, that's the news.
Oh, that's fine. You don't book too.
It's open to everything.
Oh, really?
It's not open neighbor.
Yeah.
Nobody in your office.
So I'm sure the feeling is huge.
So if you're across the room, technically you're not making.
So the difficulty caused by multiple collinearity is that it is possible to conclude that none of the individual parameters are significantly different from zero when an F-test on an overall multiple regression equation indicates significant relationship. So we're going to inflate our standard errors, and we could end up with something where our F-test tells us our relationship is significant, but all of our X variables tell us it's insignificant. That's a pretty extreme case. Furthermore, multicollinearity can cause estimated slope coefficients to be misleading. These problems are avoided when there is little correlation among independent variables. So I would focus on that paragraph that I just read to you. On page
What was that?
728. At the bottom.
The very bottom.
Second paragraph. at the bottom.
Hmm.
Remember dummy variables?
Yes.
Here's another thing, the last thing today before we go home, and we'll be here tomorrow too, if you guys want to come by, hang out again. With dummy variables, in your homework, you only had to deal with dummy variables that have the two different types of dummy variables. You had, is it Bob or is it Dave fixing it? Is it mechanical or is it electrical? You can have dummy variables that have more than two dimensional variables, descriptive variables. Let's say, for instance, we have a data set.
Then on the movie ratings, there's 4 different movie ratings, so you have to create something very for each.
Let's just say we wanted to create, here we have large, mid-size, and small. We're talking about the, must be the mid-caps of these companies, the market caps. So if we have 3 different types, this one, mine says chapter 13, it's probably chapter 15 for yours. So we have 3, we have large, mid-size, and small. We have 3 options. So if we want to use dummy variables for the size of company, if we make 3 dummy variables, our regression won't run. Because then we'll have perfect multicollinearity. We'll have everyone accounted for. We can't measure any variation in company size. So what we'll have to do is we'll have to make a large variable, and we'll have to make a mid-sized variable, and we'll have to leave out the small variable. So the way we do that,
Is that general rule of thumb, you do 1 less than the number?
yep, you do 1 less than the number up there. I think some of us, one of us, you had binary variables, right?
Oh, me for yeah.
So If column is equal to large, then 1, if not, then 0. This is going to be an indicator variable for large. And this is going to be an indicator variable for midsize if this column is equal to midsize, then 1, if not 0. And let's just run a quick regression on here just so we can talk about how to interpret these results. So we're running this average hourly wage of an employee based on the size of company. I'll put this into so look at these p-values. These p-values are not going to be significant. That's not what matters right now. What matters right now is how we're going to interpret these coefficients. So the way we interpret large, the beta value for large, is if we're comparing the hourly salary of a large company versus a small company, then if you work in a large company, then you make 60 cents less an hour. And if you work at a mid-sized company versus a small company, then you make $4.21 more an hour. So both of these are relative to the variable that we left out. Any questions? From this, we can also deduce, if these both were statistically significant, we can deduce that if large is negative and mid-size is positive, then mid-sized companies pay more than large companies as well. But that's how we interpret indicator variables or dummy variables, is we either compare it to one another or we compare it to whatever we left out as a base. Questions on those?
Which one was why? Salaried?
It doesn't really matter what was why here. We're just trying to run a quick regression.
Okay.
We called it hourly salary. I don't know.
And again, you have to pay attention to the
Next. Fine.
like that's thousands.
Yeah, the metrics. And this question is thousands. I just said it was dollar wage just to kind of get it over. Okay. So we have covered each and every type of question that will be on your midterm and your final exam.
Even the ones we skipped.
Ones we skipped were one proportion, test of two proportions without a known population standard deviation, which isn't on your midterm because it requires a template.
So what are you gonna go over tomorrow?
We're gonna go over the same questions, not the same questions, the same type of questions, different questions again. Same material, yep. And any questions people have in general? Holy shit.
What?
I think I don't. So like,
So Matt, I ran another regression with salary, and I got very different, not opposite, but I got higher with large both for the salary.
What did you choose?
So the first one, Y is always
So did you use this
I
one for
follow
Y?
you.
Or the-
This one first, and this one I run two regressions.
Okay, so I only ran this regression. So yeah, you get different numbers. Those are two different-
Yeah, I got -32. So how would you interpret this one?
This
It's
one,
not
we would just say it's
significant.
not significant in either of these. So it's just overall was a bad kind of regression. But when we looked at the other salary instead, so skip to the other one, you know,
it's like.
we found it was sort of, we found p-values for both of these, or at least for one of them.
Yes,
So we saw that large companies has a significant impact on salary.
on salary, large and mid.
Yeah.
Wait, what?
Did you want to go over?
I mean, I'm comfortable with what I got. Oh, you did. Let's just go over.
We don't take, yeah.
Someone else behind.
And it's funny because I just originally hoped that this is right, because the regression was, you know, so. Oh, I want to look at the company. Oh, no, yeah.
This is not my homework.
What's up?
What do you know?
So Matt, you know when, the other day, we remember, when we had the beta about.
Oh, I gotta go with my
You said
Chelsea.
how much it would be, such and such, so you gave us,
Sean's ill.
and we multiplied the coefficient. Here that is negative, I know that it's probably not the best type of.
Or no, I'm sorry.
No, no, it's okay if it's negative here. This is negative and beta is negative. You would say, what we're saying here is that large companies have a negative impact on salary. So what they would say is, what if a person works at a large company, what would you expect their annual salary to be? It would be 119 minus.
Like, yeah. It's weird, like you're.
It's all rolling so quiet.